Labbe. She's currently as a postdoc, or
Yes.
yeah, at Argonne National Lab, and she got her PhD from UMass Amherst. She's a real expert in fundamental chemical kinetics. Those of you that took combustion from me, I said there are people out there that study specific reactions and can spend. We are a practitioner of chemical kinetics. We use the work of Nicole and others, but folks who really understand the chemistry, and that's what her background is. So it should be an exciting talk here. She's going to talk specifically about fundamental chemistry of some bio-derived fuels and other things.
Thanks. I guess I could almost, after that introduction, introduce myself like an AA, DNA, like, hi, my name is Nicole Labbe. It's been about 24 hours since I did the potential energy surface. Like Anthony said, I am a kineticist by training. I'm a theoretical chemist. My primary role at Argonne is a theoretical chemist and a kinetic modeler. So we use chemistry as a really powerful tool to understand what's going on in applications like engines, and why emissions form from particular fuels and why they don't for other situations. And so a lot of the work that we do, a lot of the work that we do is really driven towards combustion applications. For better or for worse, if you look at the annual energy outlook from 2015, right now about 82% of all of our energy needs are met through combustion processes, and that's going to continue for the foreseeable future. It may change in terms of fuel sources, maybe less coal overall, maybe more natural gas, but that's going to prevail. And the problem with a lot of combustion applications is they're dirty. There's a lot of issues with air toxins and greenhouse gases being produced. Overwhelmingly, the CO2 produced from the energy sector is from fossil fuel combustion. And so some of having such a prevalence for combustion driven energy sources means that we have a lot to consider in terms of the problems that are associated. So as a result, there's been a ton of legislature introduced nationally and internationally to address these different problems. A couple of things addressing fuel sources itself: the Renewable Fuel Standard Act 2 and the Energy Independence and Security Act of 2007 both set minimum standards for how much biofuels need to be produced in the United States annually. And that's set to increase our total production of biofuels by a factor of 2 by 2022. And a lot of those fuels aren't just going to be corn-based ethanol. They have to be either driven from other fuel sources, like cellulosic biomass sources, or have to be advanced renewables, things that aren't ethanol. And then there's a couple other regulations, the CAFE standards, the corporate average fuel economy. So there's an agreement with the federal government and automakers to increase the corporate average fuel economy, so the overall average fuel economy of an entire fleet from a company, to 54.5 miles per gallon by 2025, and we're nowhere near that. So we're going to have to look at new engine technologies and ways to meet those standards in a very short time scale. And lastly, the Clean Power Plan was introduced by the EPA to set targets to lower emissions. Lowering CO2, NOx, and SOx by significant amounts lower from what we emitted in 2005 by 2030. So with that, there's a lot of opportunities for kinetic modeling. In terms of engine design, trying to address this corporate average fuel economy standard, we use a lot of tools like computational aided engine design, things like computational fluid dynamics coupled with reactive chemistry, to try to figure out how we can redesign an engine to be more efficient, what operating conditions will lead to better fuel economy, and how different fuels, using new biofuels, affects the heat release and the performance of an engine. With the Renewable Fuel Standard Act, we have to use chemistry to understand not just the chemistry of things like gasoline and diesel that we use today, but all these new biofuels present new challenges. You have things with fuel-bound oxygen, alcohols, ethers, things like that, which present a whole new host of possibilities of problems when it comes to fuel emissions, heat release, and challenges. So we really need to understand what the chemistry of these new fuels is. And then also related to that, identifying pollutant chemical pathways. So how are NOx and SOx formed in your engine? How is that going to change when you start going to biodiesel? How does the chemical composition of your fuel impact your overall emissions and the amount of particulate matter you may be forming? So chemical kinetic models can be a very, very valuable tool for all of these different areas. And the way that we kind of build that is to take 3 different components. We take a reaction set, which is a listing of every elementary reaction. So this isn't a global reaction. This isn't what you learned in high school chemistry, where you say combustion of methane plus 2 waters gives you CO2, or 2 oxygen gives you CO2 and water. That's not how real combustion works. The combustion of methane can undergo over 100 different elementary type reactions with dozens of species. So there's a lot of complicated networks, and we need a rate constant for every single one of those reactions. We also need thermochemistry and transport parameters for every single species that is formed as a result of burning the fuel. So what we do is we generate these large databases and we put them into some sort of solver code. We use very heavily the ChemKin combustion software suite, which has different solvers for different combustion applications, and from that we compare it to fundamental experimental data. So basically our tools for the development of these is we work very heavily with experiment. My actual experimental work is relatively small, but I work very heavily with a lot of different experimental groups, working on things like flames, low pressure flame speciation, laminar flame speeds that help us understand flame propagation, looking at things like shock tubes and rapid compression machines to figure out what the ignition delays for different fuels in different conditions are. Looking at species time histories under pyrolysis type conditions, and also things like flow reactors, looking at counterflow type speciation. We also work very heavily with different theory. State-of-the-art electronic structure theory and DFT can give us energetics of different species, different molecules, and what the barriers are for them to react. We can look at things like pathway information, looking at different tools like molecular dynamics, or MIT and Northeastern University, the reaction mechanism generator, which can automatically populate mechanisms. And then we can develop rate constants using things like transition state theory, master equation theory, where we can not only look at the temperature dependence of a reaction, but also the pressure dependence of some reactions. And then lastly, we have modeling tools where we look at combustion model codes, things like ChemKin, we can couple to computational fluid dynamics, CFD type codes. We have a lot of analysis tools at our hands, including uncertainty quantification, understanding not only what the uncertainty of the experiments are, but the models and our model assumptions and the theoretical parameters that we have input into our theoretical assessments of rate constants, and also global sensitivity, which reactions are really important in our system, which ones should we really focus on for.
Yeah. There's a light switch by the phone. And I think,
Thank you,
yeah.
Alan.
Oh, perfect. That's much better.
I knew there was one somewhere.
You know, well, I've been teaching in this room for many years.
Thank you.
And that lamp hasn't changed.
Yeah.
So developing those models are really an iterative process. We assemble our kinetic model, and then we go and we test that using these ChemKin codes against experimental data to see where we're in agreement, where we don't quite match the experimental data. And what we see the differences between our models and the experimental data to identify where inconsistencies are and what the dominating kinetics are for those inconsistencies. And then from that, we can use theory to address those rate constants, address that inconsistency, input those new rate constants back in the model, and you iterate over and over again until you get a robust model that is well validated, that you can trust. And so personally, I have quite a bit of experience in this area. I've worked on applications for heterocyclic biofuels, novel biofuels, and understanding how having oxygen and nitrogen within your fuel changes the chemistry of that fuel, and I'll get into some of that later. I've worked on hypergolic rocket propellants, propellants that as soon as you touch it with an oxidizer, they spontaneously combust. You don't need to put a spark to it, you don't need it in an oxygen environment. Looking at theoretical rate determinations for methyl plus C2 species, a lot of work on alcohol fuels. I have a robust methanol mechanism that can model high pressure and low pressure combustion situations for methanol. Worked quite a bit on ethanol, some of the ethanol work I'll talk about later. And weakly bound radicals, how quantum dynamics of weakly bound radicals can actually propagate to a difference in model observations by up to 10-12% for something like a flame speed. So, in terms of what I'm going to talk about, much of my work has been focused on looking from the small molecule, this very small single molecule size work, moving to biomolecular reactions, so multiple molecules coming together and reacting, and then moving all the way up to looking at a single component fuel and how this one fuel can undergo, in this particular case, 2,100 reactions with over 500 different distinct species, and characterizing that whole network. And my goal is to take this experience where I've been able to go from the very small to the modestly large and extrapolate up to real fuel mixture, something that you can actually model, something that you can actually get at the pump. So the first topic I'd like to talk to you about is some of the work I did on my PhD on heterocyclic biofuels. So one of the fuels we were looking at was morpholine, and it looks very similar to cyclohexane. Now, morpholine will never be found at the pump. You'll never actually burn it. In fact, it's a controlled substance because it's a precursor to morphine production, apparently. But anyways, what we were more interested in is with biomass, you end up having a lot more oxygen and nitrogen in your fuel sources. So as a result, you can end up having fuels with both of these features, and that leads to a whole host of chemistry that we need to be aware of. So we wanted to have something that was comparable to something we know well, cyclohexane, a hydrocarbon fuel that's been well studied and well understood, and compare that to the chemistry of something like morpholine, where now the dynamics are completely unknown. So the experimental work that was done in conjunction with this, I worked briefly on this particular experiment, but it's a molecular beam mass spectrometry low pressure flame experiment. So basically at very, very low pressure conditions for a premixed flame, you're able to get a pseudo steady state on the flame where radially there's very few gradients in terms of speciation. So you can sample going from the burner out to exhaust on the z-axis and determine speciation profiles. So with that, we get profiles like this, where we can see the rise of different exhaust components, such as water, as a function of distance from the burner. So we wanted to be able to understand the chemistry of that. There was actually some trouble doing the experimental data analysis of that because there were so many nitrogen species that weren't really looked at to date. So we really needed to be able to hone in on that chemistry. And to do that, we wanted to employ a chemical kinetic model. And typically there's a recipe for, especially for flame kinetics. You start with your fuel, and there's a bunch of radicals in your system. And so what they can do is they can easily pluck off a hydrogen from your fuel, and you form a radical. And then this radical can undergo a couple different things. You can have oxidation chemistry and form the RO2 type subchemistry, which is really important for ignition, not necessarily as important in actual flame or flame speciation. So what predominantly rules for low pressure flames is beta fission, which basically is you form a double bond and you break the next bond over. So this classic chemistry continues to propagate. You form a radical and unsaturated molecule. These can undergo more beta scissions and more abstractions, and that's how you fill out your network. So there is somewhat of a recipe, and so this is what you see for cyclohexane. Cyclohexane, you can pluck off a hydrogen, form the radical, and that can beta scission off, either opening the ring or to pop off another hydrogen. And then this propagates until you get to either through the ring pathway to benzene, which is a precursor towards polyaromatic hydrocarbons, which leads to soot. Or you can end up breaking down to predominantly acetylene, a C2H2 species. When you're talking about morpholine, no longer do you have 12 different CH bonds that are basically equivalent for reaction. Now you're dealing with a lot more radicals, which can undergo a lot more pathways, forming a lot more distinct isomers. And the thing is, pretty much everything from here up has never been studied. So it becomes a big challenge on how do we actually capture this chemistry and do it within a reasonable time scale. So the way that I typically approach this is you have this big network. One of the biggest things to actually explore the different relative pathways is to get that initial step, get those abstractions down accurately. And to do that, that's where I employ my theoretical chemistry background tools. I calculate the abstraction rate constants using a method called CVS-QB3, which is fairly modest in terms of computational time, but is fairly good also in thermochemistry accuracy. But then from there on, once we form those initial radicals, we used cyclohexane as an analogy. Knowing the difference between how the difference between a CC and the CO bond behaves kinetically, we can take the rate constants from the cyclohexane mechanism and use some estimation based off group additivity methods to get an estimated rate constant. And then from there, we take small molecule chemistry where there is rate constants from the literature. Nitrogen chemistry in this case, because we need fuel nitrogen chemistry in addition to NOx, we use things like the GRI mechanism, and Bill Anderson wrote a monomethyl hydrazine mechanism that I've been familiar with, so we sampled from those two primarily and other literature sources. So with that, you end up with about 2,100 reactions, and I think it was about 500 species. Over 500 of those reactions I had to come up with on my own. So once we have this model, then we can use it in our Newtonian solvers for flame applications. So there's a low pressure flame code within the Chemkin suite, and we employ that to try to model these data sets. And overall, you can see the solid lines for each of the different species from my model matches relatively well with the experimental data. We're able to capture the ultimate concentration of all of the exhaust problems. We're able to look at the rise of products and the fall of the fuel and oxygen. There's a slight shift in the model towards a burner for O2 and water, but those can be notoriously tricky in terms of the experimental data analysis. So we were very happy, and because we can get good main species, then we start looking at the more nitty-gritty, which is the intermediate species. Things that come up in very small concentrations and then quickly decompose as a product, as an intermediate species of combustion. Sometimes we do an excellent job. So on the top we have a profile for methane. The experimental measurements in the model line up very, very well. In other cases you see somewhat good agreement. So for formal radical, HCO, we do okay. We're still under predicting by about 30 to 40%, but within the error bars of this particular experiment, that is more than acceptable. So that doesn't set a red flag. But when we do find differences, such as we did for formaldehyde, then we get a little bit concerned, or in case of a modeler, we get excited. Because something's wrong, something's not right, this is an area that we can explore. So we look for opportunities where we can build these models differently. Part of one of the big sources of error for kinetics is looking at the actual fuel decomposition type chemistry, those initial abstractions and the decomposition of the radicals. And when we look at the predominant rate constants, what drives the formation destruction of formaldehyde in this case, all the reactions in red, the dominant formation pathways, come from direct products from the morpholine breakdown chemistry. So with our estimation techniques from cyclohexane, they aren't necessarily perfect. So if we really wanted to hone down and be able to reproduce that formaldehyde chemistry, these particular reactions are things that we can visit directly with theoretical chemistry. The other reactions are predominantly in the small molecule set. The small molecule set is what determines our radical pool, our heat release, our combustion products. So there has been a ton of progress in this area, but there's a lot of chemistry lacking, especially for oxygenate species, so species with oxygen in them, or species with nitrogen in them. So there's a wealth of opportunity for trying to explore some of that chemistry. And the last one is missing chemical pathways. If it's not in our model, we can't be sensitive to it, we can't test for it. So there are sometimes reactions that we haven't thought about as a community, and they need to be added in. So with that, we can integrate the flux of these different species, and we can find what the dominant kinetic pathways are. So we build these diagrams where the thicker the arrow means the more prominent the pathway. So for morphine decomposition, you can see the dominant reaction pathways, which is interesting. But if we really want to say, look at something more practical, like how NOx is formed, we can specifically look at where the nitrogen is going. So for morphine, all of the fuel breaks down into, all the nitrogen that's bound to the fuel breaks into one of these 3 different species. And what happens is these almost entirely form HCN. So you have a huge amount of HCN being generated in your flame. And so that changes how the NOx formation pathways happen, because it's very different than what you see in normal combustion. So with HCN, it predominantly reacts to form NCO. There's some other side reactions. Predominantly, if you do not go through NCO, you form NH2, and that slowly, you lose hydrogen after hydrogen until you form N atom. And then some NH actually goes through this HNO pathway, and it's either through N plus O2 or HNO, removal of a hydrogen from that you form NO, and that's the start of the NOx process. So like I said, because so much of the fuel breaks down into these CH2N type species, you have a completely different pathway for fuel-bound nitrogen that you would typically see in a normal flame with a hydrocarbon where you don't have fuel-bound nitrogen. And also you have a huge flux because you're forming so much NH through this HCN route, through HNO going to NO, which is a little bit different than what you typically see. And we were also able to model auto-ignition, so that was a low pressure, less than 0.1 atmospheres flame, but these were going to 15 to 25 atmospheres, and we still can even reproduce that chemistry, which is a little bit more practical in terms of real conditions. So we developed a mechanism, and from that we can look at the kinetic pathways. What dominates the combustion? How does things like NOx form? And how could we possibly stop that NOx? And we can look at things from a very fundamental standpoint, a low pressure flame, up to more practical, looking at ignition delays at 15, 20 atmosphere, more engine relevant conditions. But the thing is, if we want to be able to take these models and actually model a real fuel and get valuable information, we need to still do better. So identifying where there could be trouble is a really big goal of ours in the kinetics community. So I'm going to show you another example where the flame models don't match up with experiment, and in particular looking at ethanol. So we were scanning the literature a couple years ago, and this particular study caught our attention. This is a ethanol low pressure flame, just like the one we did for morphine, but for ethanol. And in the literature, there was 2 very detailed theoretical assessments of OH plus ethanol from Shu and Lin, Sivaramakrishnan et al. And so they were thought to be an accuracy of about 50%. And when you actually use their kinetics in this particular group's model, when they were trying to model the ethylene production, they got about just a little over half of what they observed as the production of ethylene. So their solution was, well, if we change one of the 3 OH plus ethanol rate constants by a factor of about 4 to 9, then they can reproduce the experimental profile, look at that must be correct, it matches the data. So what that means is, if you look at, for the implications of that, the Sivaramakrishnan et al. Study says OH plus ethanol almost entirely goes through one reaction, and that forms CH3CHOH. And the modeling study says, nope, actually CH2CH2OH has to be competitive, there's no other explanation. So as someone who has worked with theory, who really trusts our theoretical methods, this just seemed not right to me. So we started thinking, what could possibly be wrong besides the theory? And so what we thought of is, what if there's a new type of reaction, something missing that we didn't consider before? You're talking about a flame, there's lots of flame radicals, H, OH, methyl groups. And if you have a fuel radical that was able to get up to high enough concentrations, and it could react with those, could you form new pathways? And so we suggested this fuel radical, flame radical pathway. So if we look at the ethanol radicals, here are the 3 ethanol radicals of interest. In blue is the one that this theory says 95% should go through this. The red is what the modeling study says, no, it should be about 50-50. And so if you look at that particular theory-based primary radical, it's not only the dominant abstraction radical according to theory, but it's also the most stable of the three, and it takes the most energy to break that apart. So you can imagine it's going to build up to appreciable concentrations, enough where maybe these reactions can happen. So if we actually then say, okay, suppose we have a lot of this radical, what happens then? So starting from here, you have H, a common, a very high concentration flame radical, reacting with that CH3CHOH radical. And it can undergo a few different things. It can, in some cases, stabilize and go back and form ethanol. And that will happen under high pressure instances, but not necessarily in a low pressure flame. More likely, because you're already starting up from a high energy, you can actually sail across these energy barriers. So basically, if you're down here, it takes 66 kcals to react. But you're all the way up here energetically, so it doesn't have to, it can just sail straight across those barriers and go straight to reactants, products. So H plus, in this case, H plus CH3CHOH directly gives you ethylene, which was what was underpredicted, plus water. And the third option is for direct abstraction. You can form vinyl alcohol. So a colleague of ours was nice enough to do a theoretical assessment of this and calculated the rate constants for each of these individual channels. And the way we wanted to test it is, okay, we know the rate constants. We're suggesting this is possible. The only way we can really tell is if we just put it in the model and compare. So we have an in-house model that relies on the Sivaram-Krishna et al. Theoretical OH plus ethanol numbers. And when we try to model the ethylene production, the data points of the circles, the black line is our model predictions. We're under-predicting just like the Tranidol study suggested. But as soon as we add in those other rate constants, we see more than doubling of the ethylene predictions. So what we're suggesting is this type of work, these type of reactions are important. We also explored other flames like methylformate, which is a biodiesel surrogate. And we see the same types of reactions being predominant in those. And so in the original model, almost all of ethylene was formed either from that CH2, CH2OH minor channel, or through methyl plus methyl reactions giving you ethane. Once you add in the new chemistry, now you have a whole pathway through the CH3CHOH predominant radical, and as a result, you almost double your total amount of ethylene. So we propose new rate kinetics for fuel radicals and flame radicals, and we're finding these to be important in any low pressure flame situation. This might resolve some of these discrepancies that we've seen, and rather than just tuning these mechanisms, which basically cloud this type of chemistry and suggest erroneous rate constants, instead we're finding that there's things that we still don't understand, and we need to incorporate these into our models. And then the result is a significant increase in some of these intermediate species that have been problematic. So I've talked to you already about a single component fuel molecule, and looking at the smaller reactions, looking at things like biomolecular reactions and how they impact these single component fuel models. But really, we want to grow to real fuel mixtures, get to something that we can do, get some practical results from. So I've talked to you about some of these opportunities that are out there, whether it's looking at computationally aided design of engines with CFD type codes, looking at how new fuels and new fuel blends are going to impact combustion, whether it's changes in emissions, design of new fuels. What if we could use kinetic models to identify fuel structures and almost back design different fuels, saying these are the fuel structures we need, this is what works. Identifying pollutant chemical pathways. What if we could find a chemical that suppresses the major production for NOx in our particular fuel? Before you even burn it, or as you're burning it, before it even hits your exhaust, you could possibly suppress some of the NOx production in your particular fuel. So there are people out there trying to do this today, and there's some major challenges. Fuels are complex mixtures. You don't go to gasoline and get a single molecule. You're getting a mixture of dozens of different species. Many of these are huge. And a lot of fuels aren't a standard blend. You go to a pump at Shell and take a gasoline sample and go down the street 2 blocks to another gas station, they're not the same. Individual fuel components are too complex, too large for traditional electronic structure theory methods. They have high molecular weight, so we can't do the robust electronic structure methods, which have to calculate each individual electron. So we have to estimate a lot of the kinetics, which leads to a lot of uncertainties within our models. And reaction networks are so large, they can't actually be used in practical combustion modeling for like something like CFD. You're talking about, if you do some of the larger fuel networks out there, you're talking thousands of species, hundreds of thousands of reactions. It's just too big of a problem. And so a lot of approaches today are to do things like look at a surrogate model, which is an oversimplified look of a fuel. So diesel kind of ignites on the same time scale as N-heptane, even though it doesn't have the same molecular weight, doesn't have the same octane rating. The physical properties are completely different, but a lot of people use N-heptane to model diesel. I actually know of one company that uses methane to model diesel. And the use of those types of models are very, very limited. A lot of these models are over-parameterized. So like in the example of ethanol, where they adjust rate constants to try to match experimental data blindly, as a result, you cloud the real chemistry. So what works for a single type of experiment, now your model may not work in other situations, whether it's a high-pressure engine or looking at something like a flow reactor. So there's a lot of problems there. And a lot of these these surrogate models or real fuel models have a single target. They typically are only trying to reproduce something like a flame speed set and a couple of ignition delay times. So because they're so narrow, they're ignoring a lot of other chemistry, or they're over-optimizing to one specific target, which again reduces the applicability of these particular models. But there are some really great tools out there that have been developed as a process of trying to move towards real fuels, like uncertainty quantification, trying to understand where there are uncertainty and how that can direct us towards looking at improving our models, and things like mechanism reduction techniques. How do we take that 100,000 species reaction model and move it down to maybe 100 reactions that can actually be calculated within CFD type codes? So this is a figure that I borrowed from a paper from Fred Dreyer at Princeton, and so he had this idea that, well, real fuels are these long, complicated molecules. These are actually very simplified versions, but they have a lot of the same features. They have alkane chains, they have branched alkane chains, they have 6-membered rings, and they have aromatics. So what if instead of modeling each of these individually, we can model maybe individual components, smaller, much more manageable components. From that, come up with a surrogate mixture that ideally represents the fuel as a whole. And then from there, they break down to the typical small molecule chemistry we're used to. So that's kind of the idea I had for my direction of my work. And so one of the first thesis topics I have in mind is to actually say, all right, we've got a fuel component. We can look at individual components of biodiesel, for example. And using something that is called reactive molecular dynamics, actually showing in reactive fields how a particular molecule reacts and decomposes, and from there get some chemical intuitive sense of what would best represent these individual